Hi everyone. So today I'm going to talk a little bit about how to calculate acceleration. So I talked in class about acceleration and these different ideas of local acceleration and convective acceleration and then total acceleration, which is the sum of the local and the convective acceleration. So remember in the example that the local acceleration is if I had, in the way I explained it in class, you have fish swimming down a river, and if I wanted to look at the acceleration of those fish, I'd take some point here, and my local acceleration would just be the change in fish with time. And so that's an Eulerian perspective. So that local acceleration is an Eulerian perspective. But on the other hand, if I wanted to travel in something else, like suppose I had my boat floating down the river and I wanted to look at those fish, I'd have to take into account both the change in fish with time and I would also have to take into account my change in time, my speed, times the change in fish that I encountered as a function of space. So if I'm moving along here, if I'm zipping along, I'm going to have some velocity here, and that's going to lead to some change in fish with space in addition to whatever is happening there. And so this is the convective acceleration. And the local acceleration plus the convective acceleration, that whole piece there, that's the total acceleration. Okay? And this, of course, I said was a Lagrangian perspective, because I'm now moving with the fluid in my boat. Okay, so let's come back here and look at this example for a minute. So suppose I have a velocity field. This is just some made-up velocity field where I have a 2D case, an x component and a y component. So the x component is 3x plus 4 cosine t, and the y component is minus 3y plus 7x. That's an x. It's not a very good x. We'll see if I can fix it. Oh, I can't really fix it without erasing. Let me erase it. X plus 4 sine t. And what I want to do is I want to calculate the local acceleration, the convective acceleration, and the total acceleration. So how do I calculate the local acceleration? Well, that's by simply taking the partial derivative of each component. So dvx dt and dvy dt. And that's going to give me the local acceleration. So in this case, dvx dt, I take the derivative of this with respect to t. That will give me 3x, that doesn't depend on t. 4 cosine t, that will give me minus 4 sine of t. And then if I want to find dvy dt, I look here, y, x, okay, over here, that's the only thing that depends on t, so that's 4 cosine t. 4 cosine t. So a local is equal to minus 4 sine t and 4 cosine of t. Alright, so that's the local. What about the convective term? Well, the convection term is given by v dot grad v, which so that is the multidimensional analogy of this piece over here. So v dot grad v turns out to be vx times dv dx plus vy multiplied by dv dy. So notice that this piece right here, that is a tensor, right? Grad v, that's the derivative of the velocity vector, the gradient, of the velocity vector. And then I dot it out front with another velocity vector. So that's vx, and then the dot, that's why I have the ddx here, and vy dot ddy. And if this v dot grad v, if this whole idea here doesn't make sense to you, you can go ahead and work it out on your own. You can write out the matrix grad v, and then you can take the dot product with here, and you'll see that you get this back. So what we need to evaluate the convective derivative then is that first we need to take the derivative with respect to x of the whole vector and the derivative with respect to y of the whole vector, and then we need to take these dot products. So let's do that. So let's find dv dx. Well, dv dx, so we have to take the derivative of both of these with respect to x, so that's going to give us the derivative of this is 3 on top, and the derivative on bottom is going to give us a 7. All right? And then dv dy, we'll now take these with respect to y. So on the top there's nothing, so that gives us a 0, and on the bottom we have a minus 3. Now you might say to me, well, how come I don't have t that lasts here? Well, notice these are partial derivatives, so I'm ignoring everything that depends on the other parts, right? I'm only taking the part that depends on y. So that's why I only get parts with x and y here. I just wanted to point that out in case that was a question in someone's mind. All right, so now I need to find v dot grad v. I need to do vx times dvx dx. So vx is right here. So vx times dvx dx, or dv dx, excuse me. So this term, I'm talking about this term, vx times dv dx is going to be vx multiplied by these two pieces. So that will be, let me just write that out here, vx times dv dx is going to equal 3x plus 4 cosine t multiplied by 3 in the first component, and it will be vx, which is 3x plus 4 cosine t multiplied by 7. And then I need the other term, vy dv dy, and that one is going to be, now I need vy, which is minus 3y plus 7x plus 4 sine t, and now I need a 0 there, so that one will be multiplied by 0, so that one's going to go away. And then I have a minus 3 on the bottom here, so minus 3y plus 7x plus 4 sine t multiplied by minus 3. Okay, and then to get my total convective acceleration, I need to add those together. So this will be I'm going to put this, looks like well, maybe I have enough space. A convective will be down here. It'll be the sum of both of those guys. Oh, I needed 2 lines, that's why I'm out of space. I'm going to erase this, and I'm going to come do it up here. So this was that guy there. That was my local. This will be convective. I'm going to put it up here. A convective is equal to, and now what I need to do is sum these terms. So I have 3 times 3x, that's 9x, plus 7x. So 9 plus 7 is 16x, plus, and then now this has no y's, and oh, I totally forgot here, there's a 0 multiplied. Can't forget that. So this one, the first term is going to be just that guy. So it'll be 9x plus 12 cosine t. Okay, so I need to add the bottom one. So 3 times 7 is 21, and I have negative 3 times 7 is negative 21, so I get 0x in that one, so 0x plus, okay, the y's, there's no y's there. Here I have negative 3 times negative 3, that's 9y, plus 7 times 4 is 28, so I have 28 cosine t, minus 3 times 4 is 12 sine t. Okay, and then, oh, kind of ran out of space there, but you get the idea. Okay, so now I have 9y plus 28 cosine t minus 12 sine t, and this one is a 9x plus 12 cosine t. That's my convective acceleration. So now down here I want my total, which is dv dt, this is my total acceleration, plus v dot grad v, which I said was the same thing as my material derivative, big dv dt. So now what does that equal? Well, it's just the sum of this plus the local. So now my total acceleration is going to be 9x plus 12 cosine of t minus 4 sine t. And then my local acceleration is now going to be, or my total acceleration for the y component is 9y plus, and then I have 28 cosine t and a 4 here, so 32 cosine t minus 12 sine t. Oops, forgot my I, sine of t. Alright, let me just double check my notes and make sure that's right. 9, 32, 12, 9, 12 minus 4. Okay, that's correct. Alright, so that is a little bit of the math about how I calculate local, convective, and total acceleration. And the key piece, probably the hardest piece, is knowing what this v dot grad v is. So the v dot grad v is this term here, and multiply it out and get it there. Alright, that's all I got for you.